So welcome back on linear and nonlinear wave ship interactions. I'm Onno Bokhove. So the good things are from Anna Kalogiru, who's in the audience, Viaya Ambati and Wout Sveers. Anna is now at East Anglia. I'm from Leeds. This picture is for John Grew. At the end there is also a movie with John. We were arguing whether the waves in front of a ship, this happens to be a kayak, is always breaking. In this case it is, because the kayak is, oh there you are, it's going about 12-13 kilometers an hour. But they don't always break. So I promised some people, I will interrupt me at any time, I promised some people bits and pieces, and hopefully I can relate with remarks to some various talks. So the theme here, going to the question of André at the end of John's talk, was, did you use symplectic integrator? We try to do that, keep everything conservative. Can be more painful, as you will see, but the outcome of course is that you would have everything conservative, right? So that's underlying matters. So I try to do everything, we try to do everything based on variational principles. I will talk about one Clebsch variable, which is namely, with Garrett, the potential phi. And I will introduce a pre-loop variational principle. That's how I called it. And David said the previous talk about half a year ago, you didn't like that word because pre-loop was derived after loop, but it's kind of before loop. But you will see. And so on and so forth. At the end, ask me a question time, I have also a wave energy device, and it's a full variational principle with the induction mode, the water waves, nonlinear, and the buoy, the wave energy buoy coupled. Now, in the climate change report indicates that the intensity of weather will become more severe. So that's good for us, bad in general, but good for scientists. Namely, that means that water wave impact on structures is going to be more severe. So more work for us. Let's face it, it's bad, but it's more work for us. So that's the good and the bad and the ugly combined. So what are the goals and challenge? I hope I will explain fairly pedantically, I hope, but interrupt me, pre-loop variational principle for water wave, for nonlinear water waves. Show its advantage when a rigid dynamic buoy is added. A buoy being the simplest ship, just having 1 degree up and down of freedom is easiest to explain matters. Show the extension to wave-ship interaction, but derivation I won't give because it's too much algebra, but the principle is the same. Then this is between parentheses, I won't show it, but we do some discretizations, show some preliminary solutions. And I promised in my abstract, which I wrote last week, before I actually had done it, was in the middle, a very straightforward exact test solutions. So maybe it's all wrong, but then I'm speaking, so that's bad. So please comment, because as far as I know, I don't know a nonlinear wave ship or waves, this is a simple buoy, exact solution for testing. So this is due to David, he said I had to show this. So rogue waves, very nice papers by Karif and is it Diste, where a rogue wave is defined via an amplification index AI. Basically the height of the rogue wave H subscript RW over the ambient wave height HS needs to be bigger than 2. Well, that defines then a rogue wave, which you can actually get in your teacup as long as the ambient waves in your teacup are there, and your rogue wave is twice the ambient waves in your teacup. It doesn't say anything about scale. Well, this happens to be a 15-meter one, doesn't fit in your teacup. In the south of Japan, from Faulkner, it's a pyramidal rogue wave due to crossing seas. There are many explanations of rogue waves. I'm by no means an expert, but the ones which by accident, before I knew anything about rogue waves, I happened to encounter was one in the crossing seas, so that refers to the previous picture. And then, just for fun, before I knew it was a rogue wave, I actually made a rogue wave with an amplification index of 10. So it's made by removing a dam at the back, then you get a compound. So you can argue whether it's really a solitary wave, but it's after it has broken, so it's lowered, there is the solitary, where the first one reflects, boring, and then in its trough butts, you get a resonance phenomena. Now you're saying, of course, is this a wave, is this a jet? I know, and it's unfair, you have here a constriction, but you could imagine that this is a virtual wall because there is another wave coming from here, so that this acts as an effective wall. And similarly from here. So if you have C's coming from three sides, you could, doesn't happen in a real sea, two sides okay, but three sides is a bit far-fetched, but you can get it near coastlines due to underwater convergences. Andre is looking very puzzled, so. So there is actually a Kodomtsev-Petfiashvili analog. When I met Kodama, I said, Kodama, you can do this. I don't understand any of your work, but just intuitively, if instead of 2, you do 3, you can do it. So the next day at this conference in Dresden, he did it. And so he has a Setch wave of amplitude A, coming in. Another Setch wave from coming towards you, so be afraid, right? Another Setch wave coming on a certain angle, and a third one also with amplitude A coming from the symmetric angle. And then they go through each other, and for the right angle, you get an amplification index of 9, so 9A. Exact solution. And we're now, but I'm not going to talk about this, we're now putting this in the Benny-Luke and in the 3D potential flow equation codes to see whether they survive, because KP is only valid in a certain regime, right? So the question is, do these approximate solutions of water waves exacting KP survive in Benny-Luke equations or even the potential flow equations? And one student actually managed to calculate, well, I thought it was amazing, a 4th-year student, going through Kodama's theory, because we need to have the code in order to initialize, of course, the potential flow and Benny-Luke equations with the KP solution. Why do I need to do this? This Soliton Splash inspired an artist about spheres to build this steel Soliton Splash. So these are renderings, silhouettes, 2 time shots. This is a later one where it starts to collapse, and they're around the corner. We donated, and the artist is very proud, to the Newton Institute. So it's like everything, all the art is donated, so they're around the corner in what used to be, well, still the mini library. So thank you for inviting me. I didn't do that on the first slide. I arrived last Tuesday, immediately starting working. I thought I'd sit beside these Soliton splashes and get inspired. Then I realized that 9 months and 2.5 weeks is the time in my life I've spent at this institute. So thank you for the organizers, thank you for the institute. That's pretty long, right? I think that's right. So at some point I will reach an anniversary being here, right? So I'm interested in wave-ship interactions. There is a really interesting book, I think the link will work, by Rose George. It's really worthwhile reading, so the website pops out. Yeah, there it is. I will put the link in the talk when I put it online. This is really a worthwhile book if you're interested in waves and ships. She's a very good writer. Point is, look around you, your goods, 90% of what's transported is transported now with these mass container ship, right? So you don't even realize, before I read that book I didn't realize that, right? So what we do is very important. You must like that, right? But this is some backup. So okay, so I'm interested actually in a case with breaking waves, and I'm not getting to that. Maybe at the end. So Alexandru, you mentioned two-phase theory. We derived, I won't show it here, a kind of single-phase reduction of two-phase theory. So I'm wondering what kind of mathematical properties does that have, and maybe it's related to something what you do. For ships going faster, for repairs of offshore wind farms, safe seakeeping is important. You know, people get whiplash from the speeds and the impact on the waves. So mathematical modeling, we like this statement, right? Of ships, of waves is important to improve hull design, right? That's the motivation. So if we talk about impact, I'm not sure if the directors are here, this is important for, in principle, important for impact, right? We agree. So I'm going to look at this ship, The beauty of this ship is that every cross section is and take the symmetry is a triangle, right? So that's beautiful. So at first I think this is way too complicated still. So I'll just look at the triangle and it can just go up and down. That's my simplest ship. It's a symmetric ship. It's very long, right? And in essence, it's just a buoy, and you could put a vertical wall here, or it's a symmetry plane. So now the difficulty with this combination is to figure out where xp is, which is the waterline point, which is an oxymoron. But if you go out of the board, it's a waterline. But since it's symmetric, for this simple case, it's a point. Of course, for the real ship, it's everywhere. It's really a waterline around the ship. So we call this a V-shaped ship. I built it. I forgot to bring it and put it in a tank. Now you can extend this buoy to a 3D buoy in a convergence, because after I did this Bohr solid and splash experiments, I thought, well, it's nicely jacking up the wave. Well, why don't put a wave energy device there? So we built it. I saw it as a wave energy device talk, so I figure I show a little bit. So we did this in 2013 in the sweltering heat. It's not an official lab, but this is the Wout is the artist who also made the art. So we made a makeshift tank. This is really scrap heap science, right? But just to see whether anything worked. Me, the wave maker, right? Sweltering heat, getting really sweaty. It's a beer bottle later, but it's non-alcoholic beer, right? It's a full optimal control and really good, right? Yeah. But the point is, be quick. I mean, you could even disassemble it. Now there's the V, all wood, right? Still exists. I would like to have a better one, but for first testing, there's the beer, right? The beer bottle. It's non-alcoholic beer, believe it or not. This was the first attempt, just a foam. It's a piece of foam on the mast which just can go up and down. And then we used actually a linear induction. Well, it's probably not linear, but I just have to let it go. We use a shaking lamp. There's a shaking lamp. You just buy it off the shelf, and there is a magnet in there. And when you do this, it goes through the two coils and generates battery. So we figured we disassemble it, put the magnets on the mast, which goes down, and then the coils around the pipe, right? And then the thing jacks through it, and you get energy, right? I mean, and it's tape, all inefficient, just to see. Well, I guess I should make it big. You guys should have complained. We made even an Arduino scope, but is it only here? Yeah, the LED is blinking, so we're doing something. Now I thought, is this good or bad? I have no idea, but there is a patented wave energy device without the convergence, but it's just a wedge which goes up and down a wall, and that's the Berkeley wedge. I claim this one is better. You should put it in breakwaters because it focuses the waves as well. The bad Bollywood style is my thing. I told you the bad things come from me. Movies, and you can model the whole thing. So that's my wave energy part. So I will actually use in this talk 3 principles. So that's not yet the variational principle, the figurative use of the word principle. The first principle is that even when damping and wave breaking are absent, when you have a wave and a structure and a dynamic structure, the appropriate couple model should contain a conservative limit. So why not use an energy conservative formulation? And it actually simply, quote unquote, consists of the sum of the variational principles of these separate systems. If they're coupled, when you do the integration by parts, you have these things, and then you see that they're coupled. But that seems to be the simple rule. Now the third principle, which is slightly less simply as stated here, is to discretize this space-time variational principle and then vary it, and you get your numerical scheme. Semi-automatically, all quotes, right? So that's the guideline. So I looked it up again. It's nice, these short papers, right? So I did them for Journal Club. I never read Luke, and then I figured I better read Luke and read it for Journal Club. Luke states at some point, he has derived this Lagrangian, which we know. No satisfactory solution seems known for the general problem of finding suitable Lagrangian functions. And then he goes on that y kinetic minus potential, that doesn't give you the right one. Now, as it happens, Colin Cotter from Imperial and I, in 2010, in the Journal of Engineering Mathematics, there was a special volume, well, after Howell Peregrine died, we started with the kinetic minus potential energy, and then we used 1.5 Clebsch variable and 1.5 Lin constraint. Well, I mean, 1.5 is always stupid, right? But oh well. I tell you what's half. So Colin and I said, let's use a Lagrange multiplier phi to impose continuity. Let us introduce this, the correct thing. Let's introduce a Lagrange multiplier lambda to impose the kinematic condition at the free surface. That's what I call half, because phi is in the 3D interior and lambda is in the 2. It's all bollocks. They're just two multipliers. And I just have a single valued free surface, h of x, y, and t, but I keep the density at first not constant. So it's a scale density d. So you want a full density multiplied by constant rho naught. So d minus 1 is 0. D is 1. So we start with Lagrangian, kinetic minus potential energy. Then actually I have 3 Lagrange multipliers. With the pressure I impose that the density is constant, but not hard in a weak sense. With the phi, I impose continuity, right? Because if this is 0, that's the continuity equation. And here, the kinematic free surface condition at the free surface omega s is imposed with lambda. Now, if you vary with respect to u, so this is quadratically u, this is linear u, and this is the horizontal component of u, you immediately see this gives you du, take out the u, the d is going to be 1 anyway, and you see u after integration by parts of this term, u is grad phi. Yay! Oops. So phi is a Clebsch potential. It's the simplest one, but it's a Clebsch potential. And likewise at the free surface, because you have to do an integration by parts, you see actually that lambda is ds phi s, but ds is 1, so all there, right? Cool. So if we eliminate u, then we arrive at this variational principle, and by lack of a better word, I called it pre-Luke variational principle, because it's kind of before Luke, right? I mean conceptually, because if I take d as 1, I get Luke's variational principle. So depending on your interpretation of what's satisfactory, you can actually derive the Lagrangian, right? So I promised I would do David. I did promise David that I would do that. So I hope this was pedantic enough that you agree with it. And now the question is, can I use it? Yes, I can use it to look at the waterline condition. Now, by the way, Colin and I that was not the main part of the paper. That was just an exercise to get warmed up, because in that paper, which I won't show, we actually derived the model which has both the shallow water limit in it as well as the full 3D potential flow limit. So we have, by construction, the vertical component of the vorticity. That was what we set out to do. But in passing, we noticed this. So this was just a side issue. But now I can use it again, so that's good. And it shows that one can actually construct Luke's Lagrangian from, if you wish, first principles, if you call this enough of a first principle. But you can start with kinetic minus potential energy, but to got time development evolution, which is the remark Luke makes, you need to impose these extra Lin constraints, and then everything falls out. Now what's interesting, if you take the variation of pre-Luke, so now d is a free variable in the interior, the scale density, right? Only at the end, if you take the variation of p, you get d minus 1 is 0. So if you take these variations, well, the variation in p in the domain gives you d is 1. The variation of delta d, which is still free, right? It's not yet fixed, it's weakly imposed. You get actually the pressure condition, or the Bernoulli's equation, which, that's how I ordered it. This was a discussion with Ted, so you can disagree with me, Ted, it's fine. I argued this defines the pressure, right? Normally your time derivative you see in evolution. So now here you get, for delta phi in the interior, you get the continuity equation, but if you take d as 1, you get the Laplace equation, right? Which is what you expect. So it's in there. But the Lagrange multiplier ultimately takes care that everything is kosher. Then you have here the Bernoulli equation at the free surface. And of course, here you get, due to the integration of parts and so on and so forth, you get your kinematic condition at the free surface. So everybody happy that this defines P? Are you happy with that set? So the reason is, if once you take D as 1, this is a Laplace equation, you integrate the Laplace equation, so you get the interior of phi, because it links to the phi at S at the free surface, and that means that basically this you can evaluate after you do that, and then it defines the pressure. So what's nice is that the pressure comes out of this explicitly, while in Luke the pressure is minus the pressure is your integrand, for what it's worth, right? Well, I think it's worth a little bit, and we see that when we now do this buoy. And this linear buoy, linearly shaped buoy, has the following form. It resides at set is HB, which is a function of the horizontal coordinate x, and its center of mass, and then h bar is the position. Well, h bar takes care that if I'm at x is L, set minus h bar is the keel position. And I either extend it symmetrically or you put the wall here. The water depth is a vertical plane, h of x of t, so no multivaluedness. We introduce a velocity, u and w, via the velocity potential, and that's it. Now this waterline point moves, and the buoy moves. Well, it's kind of a very symmetric ship, right? But and it's implicitly defined. It's the water depth at xp equals the buoy evaluated at xp, so it's explicit. So xp is actually not an independent variable. As it turns out, its variation or its time derivative depends on the time derivative of h and the time derivative of the buoy, which equations we will derive. This gives you continuity or kinematic equation, and this is basically, and the velocity is the vertical momentum equation of the buoy. So now we take pre-Luke variational principle rather than Luke. You can also take Luke, but there's a point to this, I hope. You take it's d phi dt, right? Because I keep my scale density just free at the moment, minus m, forgive me the minus sign, otherwise I have to put the minus sign there, plus Hamiltonian. Hamiltonian is kinetic plus potential of the water waves, kinetic potential energy of the water waves, kinetic plus potential energy of the buoy. Then, of course, I have to say that the density afterwards is imposed to be unity, the scale density with the Lagrange multiplier p as before. And now what I do is, you don't need to do this, but I say, simple observation, the shape of the water needs to equal the shape of the ship where they are in contact, which is the case for x bigger than xp, so x between xp and L, right, according to this sketch. That's what you see. And xp, of course, will move. And that's all. I dumped everything in a Hamiltonian. The question is, in my definition here, the question is whether you want to do this separately, but that's just a moot point. So if you now vary 8, but now you have to take the extra variation and the variations of this extra term, and of course the coupling, then you get in the interior your Bernoulli equation, which, like I said, defines the pressure. It's defined in the whole fluid, omega. You get d is 1, of course, and you get your continuity equation, with which with d is 1 reduces to del squared phi 0, the Laplace equation. And the other variations give you the surface conditions. So delta H gives you the kinematic equation at the surface, and it has this extra term lambda, which glues the ship and the water surface, but not the free one, together for this Heaviside function for x bigger than xp, so on the side where the buoy is. So now you actually see, if you spy this, if you now take the top equation, Bernoulli's equation, evaluated at the free surface set is h, and then you see that all these terms cancel, and that you see that p equals lambda under the buoy. So lambda has a clear interpretation. It's the pressure acting on the hull of the buoy, right? Well, that's good, right? That's the interpretation. You get your kinematic equation, you get your constraint, h minus hb is 0, but only under the buoy. You get here that dz dt is w, the vertical velocity of the buoy, and you get your vertical momentum equation for your buoy, and this is just the force on the buoy due to the pressure acting on under the buoy, right? So, so as I already said, that if we consider Bernoulli's equation, well, I didn't say that part. If we consider Bernoulli's equation, so the one on the top, at the free surface, lambda is not there, because then the theta function kicks it out, and therefore P is 0 at the free surface. You get that falls out, that's this condition falls out of the variational principle, but only at the free surface. Under the buoyant, P is the pressure. That means that lambda, so lambda is the pressure on the hull, but at the waterline, if you look at the respective limits, you see that lambda at xp is 0, which is what you expect because it's the pressure, right? But this falls hard out of this pre-Luke variational principle, which is why I like pre-Luke. And maybe I make a meal of it, but Anna and I are not quite sure whether we totally agree on the interpretation. I think this one is okay. But I haven't imposed here that lambda is 0 at the waterline. Lambda is fully free. Huh? And it imposes this constraint also at the waterline, in this pre-Luke variational principle. And then as a consequence of all the variations, I get my conditions, right? So it's like a bit of the chicken and the egg game, right? Because what happens, okay, a little bit further, why do we need one? Well, because lambda, like the pressure, satisfies an elliptic equation under the buoy. And the way you get that, let us consider the constraint or minus the constraint and say, of course, it needs to be preserved in time under the dynamics. So you need to take the time derivative of that equation in the line above 10. So you take the time derivative, use the equations of motion, and you get the blue underlined term, which in Dirac's constraint theory, but doesn't really matter, it's a secondary constraint. Well, it's a second constraint. There's no arguing about it. It is. So you also have to insist that that one stays put in time for consistency. Well, when you do that, you take the time derivative of this to the, what is the chain rule, and then dWt, oh, I already did that there, and then after some rearranging, you get the elliptic equation for lambda under the buoy at the free surface with the right-hand side, which is the total flux. You recognize this as half u squared plus half gh. But I might have done the half wrong. But anyway, I think the half shouldn't be there. Minus g. Elliptic equation needs a boundary condition, but I just derived that, so that's good. Right? So I'm happy, right? When I did this last week, finally I was happy. Actually, I half did this earlier. But now there is the problem, which I find the chicken and the egg problem. If I take d as 1 in my pre-Luke with buoy, so this was the pre-Lucas buoy, then I expect to get, I've gotten rid of d, and I kind of have Luke's variational principle plus the buoy motion combined, right? Seems logical from what I explained before, right? But now there is a problem. I don't get this condition out of my variational principle. So the only thing I could imagine doing, but you can disagree with me, but it changes a bit, is that I impose, so on the function space, so Alexandros should now be happy, so lambda has a function space, but now I have to impose that lambda at the waterline is 0, because I can't get it out of the variational principle anymore. Seems logical, right? A priori, because it doesn't follow otherwise, because I have no pressure equation anymore. That's what I liked about pre-Luke, right? I got it all for free, and I don't get it for free anymore. I have to impose it. So logical, but it's something one has to think about. But now there's a catch, and Anna and I like, that's me, right? Not Anna. Anna's deep, calm voice, right? And because there is now a problem. If I a priori impose that lambda is 0, then h minus hb is not imposed at the waterline. While before, I made that point explicitly, in pre-Luke, lambda wasn't 0 yet. Now I have to impose it a priori. So, well, this is important in the numerics. So it's all logical, but whether it's what the implications are, I actually don't know. For one point, the limits are okay, but at one point you're not imposing the constraint. And I've, quite honest, well, we're still bickering about it. So prelook in some sense is nice, and that's why I thought it was worthwhile looking at prelook. So Van Dalen and Goossen and Dingemans in 93, that's correct, right? I know 93, derived the equivalent of the above for a full ship with the 6 degrees of freedom, rotations and translations, but didn't use a Lagrange multiplier. They required the use of something which I, for the longest time, found a mystery, variational Reynolds theorem. Big statement. We derived it, not I, but the previous team derived it at some point for something, and they do it for a simply connected fluid domain, but the free surface and also the ship can be multi-valued in Z, while we have limited ourselves to everything being single-valued in Z, the hull as well as the free surface. Now you get their equations from our part if we substitute lambda in the equations, but this time derivative is tedious, and we didn't want the extra time derivative in the equations, because for the time discretization it's awkward. Now an ansatz is that this multiplier approach can be extended to the multi-valued case, so either the ship or the free surface shape, by using fixed reference coordinates. Now Bridges and Donaldson, without a ship or buoy, go in this direction, and then one basically uses the underlying reference coordinates which underlie the proof of the variational Reynolds theorem. It actually relates, I realized this morning, to what you guys do, because in some sense you go back to a nice reference coordinates, right? And then you get extra terms from your Jacobians, and this would be an extension where you include the ship, but rather than having a rectangle, I think you should take the rest shape of the domain, so with the ship indenting as your reference set. I think that's more logical. So I think there is some mileage in, well, now in looking in detail what you guys are doing, because it might be useful here. So since we want to start with the linearization, we linearize now prelook around the state of rest. So we introduce d as 1 plus d tilde. H is not a constant, it's a constant at the free surface, but under the ship it has the shape of the rest state of the ship, h of x, and etc. And of course the pressure is the hydrostatic pressure in the rest state plus the p tilde. So now this boundary condition on the waterline, you need to use a Taylor expansion. At rest, the rest state lambda is of course 0 at the waterline. This is the linearized waterline, because you expand around LP plus x tilde LP, where x tilde LP is small. Now if this is 0, then this defines lambda tilde in terms of xp, but like I said, or x tilde p is not independent. If you expand the shape of the ship, so this was h at LP to first order, you can actually relate xp to the perturbed position of the buoy, set tilde, and the perturbed free surface under the buoy, and this you substitute in there, and then of course you get lambda tilde at the fixed LP. So this is the linearized condition. Of course, lambda tilde is no longer 0 in this case. And that's similar to linear theory for a free surface. When you take linear theory for a free surface at the fixed top level, at the reference level, you get that the perturbed pressure is g eta. So this is the equivalent for the masses under the buoy. Now the problem is, which probably is obvious for analysts, I'm again referring to Alexandru, but there are probably more of you in there. So I thought, how on earth am I going to impose this in my variational principle? What am I going to do? And then I remembered, I think, an old class in elliptic equations. Well, what you do is, I want a new variable which is 0 at the linearized fixed waterline. So I just subtract, I decompose it, and that's it. And I have a new variable, because that's easy. Because the problem is, this is not a constant, that condition, but it's depending on the variables, depending on time. So that, when you do that, you can actually, when you do that on the equations, that's the order to do it. You get the linearized equations. You nicely see that p tilde is mu tilde plus this perturbation. Now you say, oh, that's not good. There's an extra term, but remember, this is 0 under the buoy afterwards. And then going backwards, you can derive the variational principle, which now, for the linearized system, which now totally only consist out of quadratic quantities, because if you take the variation of a variational principle which is quadratic, you get the linearized equation, and this is the crucial term. This is an extra kind of penalty term, if you want, although I hate that term, which you need to express everything in mu tilde, and mu tilde is 0 at LP by construction. And hitherto we hadn't used that. So here it says you get the normal condition at the free surface, that the perturbation pressure is G eta, but under the buoy it's G eta plus lambda tilde, and lambda tilde we have decomposed as such that the elliptic equation for mu tilde again has a 0 at the linearized water line. So now you can all do this for the ship. There's no problem. The whole thing, but it's much more elaborate. You need to introduce the center of mass, the angles. You use pitch, roll, yaw rotation convention, because that linearizes nicely the moments of inertia, the angular velocities, and it is what I said before. It's the kinetic energy of the water. It's the kinetic and potential, and the kinetic and rotational and potential energy of the ship with all its degrees of freedom. And now I have actually glued it together with a new concept, an inequality constraint. So now I do it over my whole surface, but as it turns out, if you take the variation of lambda times mu squared, you get the following. So all the rest is the same. This is different. If I take the variation of delta mu, I get 2 mu times lambda is 0. Well, that only has two possibilities, right? Mu is 0 or lambda is 0. Life can be simple sometimes. So it's mu is 0 under the ship, and its lambda is 0 at the free surface. So what's in principle nice about this is that I don't specify the waterline point. It falls out of the solution because it's where mu is 0 transits to mu is non-zero, or vice versa, lambda is 0 transits to lambda is non-zero under the buoy. I mean, sounds all. And then you get the rest of the equations. You get your momentum equations in x, y, z, and you get here your rotation, the angular momenta equations of the ship. But for this case, the ship needs to have a simple shallow hole shape, so no multivaluedness. And the ansatz is again thinking about you, but also thinking about I always think about Andre, and I'm kidding. Going to reference coordinates might help you here as well. That's the ansatz. So the numerics, very briefly, we use finite elements in Firedrake or MATLAB. It's an automated environment for finite elements. Developed at Imperial College. By the way, nonlinear 3D potential flow without ship and the Benny-Luke equation is freeware. Well, the potential flow will be online soon. The Benny-Luke is already online. So what we actually seek, going back to the beginning or the end of John's talk, a geometric symplectic space-time discretization. And the precursors, and some about the ship is in these papers, which I refer at the end. And our first attempt hitherto is basically use molecular dynamics techniques of molecules which have fixed distance because they have a constraint. Just use the same technology, and Colin is again mentioned here. That's what we have solved hitherto. An alternative, in which case the elliptic equation, either in the linearized case or the nonlinear case, so mu tilde or lambda, are hidden in your formulation. Alternative is to explicitly solve the elliptic equations first. Inequality constraint is beautiful because you don't have to calculate the waterline point. It would, in principle, come out of it. That's in progress. All the alternative is go to reference coordinates, which we didn't really explore yet. So now all the results are linear, and part of the linear bit still need to fix because I fixed it the other day. But just let us now it's the movie part of the talk, so let's go to the movie part. So this is a wave maker case. And then there is a convergence at the end, this phi convergence, but the walls are not shown, but you will see that this wedge, is it a tetrahedron? I'm so bad in this shape. Is it, what shape is it? With the four corners? Yeah, the tetrahedra is the wave energy defined, and it can only go up and down. And you see the waterline motion. So this kind of standing waves. The wave energy, there's no wave energy extracted. It's just doing its thing. So well, what's the point of this? The point of it, here is plotted for actually the sluice gate case after the sluice gate has been pulled out. This is time. This is the energy in the water, which is constant. Then once it starts interacting with this tetrahedra, it exchanges energy, and you see that. And here's the energy in the buoy. It gets hit by the wave and it starts doing its thing. The energy is transferred, but then the total energy, so the sum of the two minus the initial energy at some time after the sluice gate has been removed, is much smaller. And if you half the time step, this goes down by a factor 4 because we have a fourth order integrator. So there's no drift in energy, which was the point of the whole total conservative integration, and that's what these integrators take care of. This was, by the way, for shallow water and a buoy, so I didn't explain shallow water. This is comparison between shallow water and a buoy and potential flow model. So potential flow in the long wave limit, so you can make a comparison. So they compare reasonably well. All right. So here's the same. This is we built it up gradually, right? So now we increase the degrees of freedom. We look at the 2D ship, which can rotate, go up and down, and also go whatever it does, right? So here again is energy in the water, energy in the ship, the 2D ship, and then the sum is much smaller. And if you decrease the time step by half, that will go down by a factor 4 because it's a second order method. This is the sluice gate case. So it's the wedged ship, and now you have two water line points, right? Or water lines if you extend it, and it does its thing. So everything is on YouTube. We'll give the link at the end. So this is a 3D wave tank with this ship in the tank. So let me show the. So you can define this whole ship. This is from the top, and this is a V-shaped ship. The dashed line indicates the weathered area when it's at rest. So here's the compressed ship in the top when a wave maker is making a wave, and then it meets the ship. And this is actually what the ship does in its proper aspect ratio. The ship there was a bit shorter because of the plotting. And then the blue dots are there. It's not a smoothed particle method, but the blue dots are water particles, just to indicate what's happening. And this is almost symmetric setup, so there is no, I forgot which one is this word. Is it the picture there? There's no shaking of the ship in that direction. It's the minus Q as it should be in a symmetric setup. All right, well, one issue we have, and other people have as well, I don't have an exact solution of the two things, even for the buoy. So the first thing I tried, and I failed miserably, is I thought you may or may not know these solutions of Ball and others where you have shallow water equations in a parabolic bowl, right? So, and then the velocity profile is linear. U is u naught of t times x. This is a parabolic topography, and then the free surface just this, and then it goes down, and it does this at a later time. And you can derive the ODE for that case, and by quadratures you can integrate exactly. So I thought, let's do this. Let's put a parabolic buoy in a parabolic ball, and then see if I and then here again have this parabolic free surface shape, and see if I can connect everything together. But I failed. Well, it might mean that it's not possible. I failed to impose the proper continuity in H and U together. So then I invented just last week, I thought about even simpler one. It's so ridiculously simple, but you still end up solving cubic equations. It's laughable, but nonetheless, it's there. So I take a symmetric setup in the shallow water equations, 1D, so only in x direction, steady with the buoy, my infamous buoy, right? But now water can go in and can go out. So in some sense, it's symmetric with another waterline points of one at xp and one at 2L minus xp. And now, maybe you know, I teach that in class, maybe you know the very famous solution, certainly Ted knows it, of shallow water flow over a hill. Right? It's from Houghton and Kasahara. And this has, so in a certain case, if you define an upstream fruit number, either the free surface goes up when f naught, which is a constant, is bigger than 1, which is the upstream fruit number, so it's the upstream flow speed constant, divided by the square root of gh naught, with this being h naught. But if you dimensionalize, you scale it to 1, and u naught, you also can scale to 1 if you all put it in a parameter f naught. And then for the subcritical case, it dips down. And it's symmetric. And then it comes out, and this only exists for certain f naught. So I thought, my buoy is kind of an upside down hill, so let's try whether I can do this. So let's just try, right? I thought it didn't seem to be a bad idea. But what will happen is, where it is will react, right? So you expect for subcritical it to go down. So what do you solve? You solve it can't be more simple, right? But that's ddx of hu is 0, so hu is 1 if you don't non-dimensionalize. U and h are 1 upstream and downstream, so that's easy. You can eliminate u. The second equation is the Bernoulli equation, but now under the buoy, so I have a lambda there, which is the extra ingredient. So then you can eliminate h, you can eliminate lambda and put it in here. And now, given that you know the shape of the buoy and therefore the free surface under the buoy, you can eliminate h. You can also find where xp is, because that connects to the height 1 at the upstream side. So the only thing which remains is actually the unknown position of the buoy. That's why there are all these brackets. I first eliminate u, then I eliminate h and xp, so I have only what I want to determine is set for a given upstream fruit number. That gives you a cubic. It always gives you a cubic, as Ted can attest, but now a cubic in the center of mass set. Believe me or not, this is a cubic, which is 0, and and a function of f naught. And you can. It's ridiculously simple in the end, but this is set, the position of the center of mass, and this is the position of the keel for the range of fruit numbers for which a solution exists. And I could not find one for the supercritical case. So now this critical fruit number you find as follows. I said I had the cubic. So then, of course, the first thing you take is you take the derivative of the cubic to determine the point where it has a local maximum. Because where the cubic and you see that I put it at the edge there. If for another fruit number the cubic goes above 0 and has 2 zeros. One is the valid 0, and the critical fruit number is the one for which it just touches 0. So it's very, very simple, and that gives you here indeed what is 0.38 or whatever it is, which is exactly the end of this thing. Ridiculously simple, but still a stupid cubic to solve, right? So now I wondered the following, right? I mean, but here you need some boating experience. Could one do this for a case which is not fixed up and down, and it can also rotate, but cannot translate in the x direction, for an asymmetric wedge? I'm getting all excited, right? I don't like speedboats, but I do like sailing boats. But still, I do like the maths of it. So that's an asymmetric wedge, where then it goes, and I refuse to use the English word plane, in plane, for the supercritical case. I wonder whether you can find the steady state exact solution for that for fast, high enough fruit numbers. So So they shouldn't be too complicated, but now you have 2 degrees of freedom, so I expect a coupled system in terms of the angle, which will be fixed at steady state, and its vertical position, so it will be more complicated. Of course, I haven't talked about the stability, but at least I managed to find one exact solution to test against the numerics in a nonlinear case, so that's good. And you can, of course, also linearize to use it for as a check. So that finishes this journey. So we modeled the linear wave energy device, modeled I modeled the nonlinear formulation, and numerically we did parts of the linear bit. Next steps are to fix this linearized boundary condition, the nonlinear coupling, and then a mixture theory. So Anna and I derived a mixture theory a model for wave breaking from the two-phase model, from a two-phase model. It reduces to a single-phase model, but the important is that it has as limit the full potential flow in it. So we try to actually make a numerical model where the potential flow limit is nicely embedded and conservative in there, but when there is wave breaking, you get extra regularization terms. We did the same actually for with the student Mark Helmerson for wave flexible elastic turbine mass, both hyperelastic and elastic, the full variational coupling. Here are a couple of references. I promised someone, was it Garrett? So I found in a book, this guy from Ireland, Wellstead, the wave energy device, the induction motor. So M is the magnet, right, like in the wave energy device, but if it should be tilted, the picture. It goes up and down, and actually the only terms you need to add to the variational principles, you have the water wave part in the dots, right, the important dots. Then here this should be plus sign. Here the part of the wave energy buoy, and then you have to add these terms, so the induction, which is a function of the Z position, the current, and Q. What's Q? My Q is the QDT is the current, so Q is whatever it is, and it's nonlinear in set. So I discussed this with somebody. It's a nonlinear variational principle, and it couples the whole lot. The magnetic part, the induction, right? This is the voltage output, the wave and the buoy combined. Now, I have to finish. I have to make John happy. So you don't want to anger John. This is where we went slow in the double, and there was no wave breaking. That's it, guys. This was in winter, so we were cold. But anyway, thank you very much.
Now open to questions and comments.
Okay. Okay. Well, I can't resist since you discuss this breaking. You will always have breaking at this when you have this angle. You will always have breaking there.
It should be like this.
No. We in your device, because it's a weak singularity. It's a singularity mathematically. It's a singularity at the intersection.
Well, I mean,
you
no, with the ship you have a power like that.
With your device, you will always have breaking. It's much clearer to take it vertical. Then you reduce the singularity. You have a mathematical singularity when you have a slope on your geometry.
So you're telling me my exact solution doesn't work?
I'm saying that in reality it's a breaking there. You have a mathematical singularity there, and that is weaker if you take it vertical. Then you reduce it.
All right. Derek?
Along the same lines, if you have a vertical surface, you know that your solution will be unique.
Mm-hmm.
I'm not sure that it's unique if it's sloping. At least nobody's proved it to be unique. So going back to your Lagrangian, does that hold even when the barotropic approximation isn't valid?
Which Lagrangian?
Free loop,
With the buoy.
with or without, doesn't matter.
Or is it without? Is it without? Yes.
Does that require a barotropic approximation or not?
No. This is fully 3D. As it said, the x, the y, the z. It doesn't. It's just like loop, but it's one step before in the derivation. This is loop, dx, dy, dc, dt, and this is pre-loop. It's just the density is not, it's imposed weakly as a constraint rather than as a hard constraint. Right? So like I said, if you take v as 1 and 5, you get loop. But the advantage is that you get the pressure as well, explicitly in it. So there is no barotropic approximation here. It's fully 3D.
Any other questions? More questions? Okay, so thank you very much.